So when it comes to coronavirus data, I think just in general, a lot of people are confused about what certain things mean. So here's kind of like a basic understanding of what's going on with coronavirus. So the first thing that you're probably hearing a lot of is coronavirus is spreading exponentially. And sometimes that can be a little bit hard to understand. So a very basic representation of something that's exponential is, I mean, there's tons of different examples. A really common one that you might think of is when people share stuff on social media and it goes viral, like a virus, like coronavirus. So for example, if someone posts a video, change it to the pen, someone posts a video and then two people share it, and then those two people share it, and then each of those two people share it, to two more people and you keep sending it to people and people and people, you can see how this is getting very big very quickly. Okay. And so on. I'm not going to keep doing it. But so you started with one person who sent it to two people, which then it went to four people, then it went to eight people, then it went to 16 people, and so on. And it gets very big. And when something goes viral, it's obviously up to, the hundreds of thousands or the millions of people that see it. So it spreads very quickly, much like the virus. So really what's happening here is every time it's multiplying by two. And obviously this can be a different number. It could multiply by three every time. You could share with three people, you could share with four people, and then it gets bigger and bigger and bigger, depending on how many people you share it with. So that's the basic thing there. When you look at an actual calculation of an exponential function, you might see something that looks like this. Oops, y equals 2 to the x. So here's an example of an exponential function. You can see it starts very close to 0, and then it shoots up very quickly. So all the way over here, it's basically close to 0 on the y-axis. Then between 0 and 10, we can't even see it get to 10. It goes up so quickly. So zoom out and you can see that it just shoots up and shoots up and shoots up. So you've probably heard the term flattening the curve by now. Okay, so flattening the curve, that's when we start thinking about what can we do to reverse this exponential growth. Okay, the opposite of exponentials is logarithms. So think of we are learning about logarithms right now in Math 3, and I know it's really hard to wrap your head around. So think of like your basic operations. The opposite of adding is subtracting. Okay, so when we say 3 plus 4 equals 7, we also know that 7 minus 4 equals 3. I did the opposite. Same thing with multiplication and division. They're opposites of one another. That was a very bad division sign. Here we go. So for example, you have 3 times 4 equals 12. Well, you also know that 12 divided by 4 equals 3. Okay, so we can see how those are opposites of one another. Same thing with exponentials. If you have something raised to the x power, like 2 to the x, well, the opposite of that would be taking something called the logarithm. So you see this log here. So think of it as just an opposite operation. So looking at a calculator, we know what an exponential looks like now. Well, what if I type in a logarithm, which I have to select from one of my functions here. I do log base 2 of x now. Now you can see that you have the exact opposite. That's because these are inverse functions. So now your curve has been flattened, okay? It's not growing quite as much. It grows really quickly at the beginning and then it slows down. We flatten the curve. Logarithms actually have an asymptote. So there is some imaginary line here that this graph is approaching and it will never cross, which is great because, for example, we don't want our hospitals to be at capacity. There's some capacity there that we want to stop it at. We don't want it to cross that line. That's why you keep hearing about flattening the curve. So really, if you want to actually model the growth of this pandemic, neither one of these functions actually does the trick because we don't want it to be exponential. We don't want it to keep going and going and going forever. And obviously, there's some exponential component to it, so the logarithmic one doesn't work either. So neither of these works. So there's actually a different type of function that we don't really learn about in Math 3, but there's a different type of function that actually is better at modeling pandemics. Right now, the data isn't quite following this particular type of graph, but I'm going to show you some data from a previous pandemic. Actually, this other curve called the logistic growth that more so can model pandemics. So on the left, you see exponential growth. There's nothing stopping it. There's no curve that's been flattened. We talk about logistic growth. I'm not actually going to get into the explanation of the uh, equation that's behind logistic growth because it's a little complicated. There is a natural log involved. But now you have this exponential growth, but then the curve is flattened, okay, and it actually starts modeling this way. So we don't reach this capacity. There's still that asymptote like there was on the logarithm that stops the graph from continuing to grow. Thing that's come up a lot when it comes to COVID is that people are making predictions. They say, okay, on this date, this is how many cases there will be. This is when it will be bad. This on this day, this many people will die. Stuff like that. So how the heck do they do that? So a very, very basic example of this. Think back to probably in middle school. You guys talked about scatter plots. So for example, you have some graph. Sorry, I'm drawing with my mouse, so it's not great. You have some graph, and there's some data. Okay, you have these data points. This could represent pretty much anything. Um, but you have these data points, and then you were asked to draw a line of best fit. So you drew a line that you thought fit the data pretty well. Okay, so that's called finding the line of best fit. There's actually something called linear regression where you can truly find the line of best fit, and it can actually help you predict what's going to happen in the future. So what happens is your computer essentially measures the distance. This is not something you do by hand. The computer basically measures the distance between each dot and the line and tries to kind of average it out. And depending on how close it is to the line, some things are truly linear. They get this value called an R squared value, and if it's close to 1, it means that it's a pretty dang good line of fit. So that is how we can actually make predictions because sometimes you have data, you maybe only have this part of the data, but now I can make this line of best fit, and now I can say, well, if this axis is time, I can say now, okay, if this is April 1st, I can say, well, I know that by April 10th, or whatever day this is, the 10th, there's going to be this many cases of coronavirus, or whatever data we're talking about. The problem is with coronavirus, it's not linear. So what I created here on just an Excel spreadsheet, I used data from the CDC, so that's what you see over here on the left. That's our government department that deals with disease control. And I just did data from the 15th of March to the 31st of March. I didn't go into April at all. And here you see the number of cases per day in the US. I know there's like a ton of issues with the data that we're being given just because there's not a ton of testing. Not everyone that has coronavirus gets tested because maybe they don't have it so bad or whatever the situation is. But nonetheless, you still kind of get an idea. So what I did then was then plot it over here on my graph. And you can see that you kind of have this curve here that's going up. Think back to our Desmos thing over here. I'm going to erase the green one. This exponential function that we had where it goes up. This one goes up super rapidly. We're not quite at that yet in our particular data that I'm looking at, but it also kind of depends on how you set up the graph. So this is just between 15th of March to the beginning of April. Now the graph has definitely curved up quite a bit more. Okay, we have way more cases now coming into April. But you can see there that there is that little curve that's going up that's showing that this is spreading exponentially. And it's kind of cool how they line up so well. I mean, it's sad considering the situation, but it is crazy how closely it mimics an exponential curve. Something that I think has been confusing to people when it comes to looking at COVID data is the use of logarithmic scales. So I just found this picture explaining the Richter scale online. This is an example of a logarithmic scale that you've probably been exposed to a lot. Not that we have earthquakes in Kansas, but you've heard about this on the news. So the Richter scale, this is how they measure the magnitude of earthquakes. So for example, you might hear, well, it's a 5.2 magnitude earthquake or an 8.2 magnitude earthquake or whatever. The interesting thing about the Richter scale is it is a logarithmic scale. So every every measure of magnitude is 10 times stronger than the previous one. So in this particular chart, it shows you about how much dynamite is equal to the energy in the Richter scale. So you can see how it's increasing a lot. And between 0 and 1, it's only 20 kilograms of dynamite. Uh, and the second one, it already goes up to 600. Third magnitude is already up to 20,000. Fourth magnitude is already up to 60,000. Then it goes up to 20 million, and it keeps going and going and gets very big very quickly. Okay, so every scale of magnitude on the Richter scale is 10 times stronger than the previous one. So it's kind of confusing because we don't think of things as not being linear very often, but it is useful because you can see that there is this constant amount of growth. So on the data, back to this Excel sheet, I did go ahead and add in the stuff from April here so you can see that you have this exponential growth. Sometimes the data that's being presented on the news actually uses a logarithmic scale. So again, going back to what I said about exponentials and logarithms being reverses of one another, they kind of cancel each other out. So currently you have a linear scale along the x-axis. This is day by day, okay? Every little mark here is 5 days. On the y-axis right now, every mark is 50,000 deaths. Excuse me, not deaths, cases. Okay, so 50,000 cases going up of coronavirus. So this is also a linear scale. Then your actual chart is exponential. It's going up exponentially. So sometimes on the news or whatever, you'll see a graph that actually has a logarithmic scale like the Richter scale, where each chart or each space on it is 10 times stronger than the previous one. So for example, I can actually change that on my graph here. So if I change this to have a logarithmic scale, now you see on the y-axis you have what? 1, 10, 100, 1,000, 10,000 cases, 100,000 cases, 1 million cases. And now your exponential chart is actually more similar to a line. Okay, so the linearness canceled out. So the exponential became a linear one when I used that logarithm to cancel out the exponential side of the graph. This is useful because now you can see there's this constant state of growth. That's what linear functions are useful for. They're very constant. Now you can see this constant rate of growth. And this is also useful for making predictions, like I was mentioning earlier when you talk about line of best fit. So that's a basic overview of the data that you look at with COVID. Hopefully that explains some of the stuff a little bit more. Some of the logarithmic charts that you'll see will not be as dramatic as this one, but just keep an eye out because sometimes you think, well, that chart's wrong. It might not necessarily be wrong. It's just trying to show something different.